Germany is a leading industrial nation, but still has many areas that desperately lag behind on the telecoms front. And that applies to both landlines and internet access. Though broadband speed rankings constantly fluctuate, Germany ranks in the mid-30s compared to other countries. And while other countries pick up the pace, Germany is struggling to keep up. Might one solution be an extraterrestrial one, providing high-speed internet for everyone? The Earth's orbit will soon be home to new constellations of satellites in the thousands. Could they make the vision of fast connectivity everywhere on Earth a reality?
And we have confirmation of deploy.
Which regions in Germany have the worst internet connection, and how is performance measured? The engineering consultancy group P3 specializes in gauging the signal strength of networks for mobile phone and internet providers. Its fleet of several dozen cars ferries its specialists all across Europe to detect any gaps in coverage. The technicians measure the surfing speed of various websites, including the up and download of data and video streaming. Aborted transfers and sluggish, intermittent connectivity indicate deficits in network quality.
The
phones are being connected to a computer where a sound file is being played. The first phone calls the second one. Once that call is over, there's a brief pause, and then the second phone calls the first one. And that's repeated all day long, so as to objectively determine the voice quality.
The team also use speed test websites to check DSL and landline connections on millions of computers worldwide. That enables Olaf Gerwig, Thomas Prefi and their fellow engineers in Aachen to give providers an overview of global networks. The information reveals how well or poorly competitors are performing.
This is data gathered from users around the world. We've developed a piece of software that is integrated in around 900 apps. And these apps are installed on around 200 million devices worldwide. When users agree to be involved in network quality assessment, this app will register the actual user experience. Wherever the user is using their device to download material or view videos, we can see in the background how good the network coverage was, whether it was 3G or 4G, which country, which provider, and a lot of other information. We get our information not via the users, but via the networks.
The biggest bottlenecks in coverage within Germany are in the east of the country, but some of the worst internet connection is down in the southwest, in the area around the town of Bad Säckingen. Jürgen Albitz has teamed up with other local residents calling for free internet. And the local authorities are also helping to set up Wi-Fi hotspots across the area. The only alternative is to use mobile phone providers across the border in Switzerland, albeit at a price.
Coverage from Switzerland is great here. I have a weak signal for a German network and strong signals for two Swiss ones. Being unable to access data while on the road is a major problem for companies. I can't do after-sales or carry out jobs or orders. I can't give my clients any information. And the emergency services can't get the data and information they need to help people who've had an accident.
Some areas here are so remote that network providers are reluctant to invest in installing broadband cables. And that includes places along some of Germany's highways and other non-urban roads.
So you can't use the time on the road for a couple of phone conversations because the call will cut out every 2 or 3 minutes. So you have to reconnect. It's not worth it. People who have an accident out here might get lucky and pick up a couple of radio waves. Otherwise, they have to walk to the next inhabited building and ask for assistance. Basically, like in the year 1900.
Those beautiful landscapes can also cause major headaches when it comes to expanding network coverage.
The problem is the topography. Bad Säckingen is in a valley surrounded by the Black Forest Hills, features that are unfavorable for network planners. And it's practically impossible to provide that density of coverage with conventional technology.
And here too, there are companies that are completely dependent on fast broadband connections to the rest of the world. Espaço Software specializes in the digitalization of the global working world, providing solutions for shift schedules and interactive management. Bad Säckingen is home to both the company's R&D department and its global sales division. The company would have had to close its premises in the town had it not been for some smart solutions devised by its own developers.
We have video conferences here every day, online presentations, remote system configurations, and online training sessions. And that requires a fast internet connection. Our founder and director, Andreas Eschbach, is based in Boston in the US. So we also need a good connection to that office too. We have this hunger for data, and it's growing every day.
Down in the basement, the software engineers managed to solve their internet problem by combining a range of different elements.
We've linked up a number of internet connections, a DSL line, a cable connection, and we're now planning to throw a third anchor across the Swiss border. Basically, there's an excellent LTE network just a few hundred meters away, and we're linking up all these lines to create a very fast internet connection.
Technical obstacles alone mean that makeshift solutions like this are not an option for private individuals, and that's a gap that Jürgen Albitz wants to fill. He and his fellow free internet activists have installed free Wi-Fi in most public buildings in Bad Säckingen.
Hallo? Ja, super. Glasklarer Empfang.
That's a crystal clear reception.
The
big network providers, or most of them, offer customers a voice-over IP option. The advantage there is that people can then make phone calls via Wi-Fi. So, with the right contract, you can now phone people for free via internet.
Bad Säckingen already has dozens of free internet terminals, enabling local people to surf and make phone calls. Jürgen Albitz has set his sights even higher, however, on fiber in the sky, a fast internet connection via satellite.
Fiber in the sky is
definitely an option. It avoids the need to dig up roads everywhere, which is what prevents network expansion. Providing the right bandwidth here via fiber optic cables means laying 3, 4, or 5 kilometers of cables. That's extremely expensive in a hilly area with hard ground. Fiber in the sky comes from above. Everyone has their own direct receiver and high-speed internet.
Kourou in French Guiana is the launch pad for Airbus and Arianespace satellites. They orbit the Earth at an altitude of 36,000 kilometers and always above the same point. They serve primarily to transfer TV and radio broadcasts. The geostationary communications satellites are assembled in Toulouse, France. They weigh up to 6 tons and have an operating life of 25 years. Each satellite is highly complex and custom-built and can cost up to 250 million euros. And that's why current satellite-based internet connections are so expensive. Demand for this option, however, is continually on the rise. Varinka Ponomala has been part of a revolution in satellite design in recent years, from individual components to mass production.
In fact, today, from the design to the delivery to the customer, we can provide satellites in less than 2 years. For us, it's quite short.
An innovation in power technology systems heralded a new era in satellite construction.
For satellites, Airbus developed electric propulsion. So it's for us a big gain in terms of mass at launch, and it allows us to have more equipment on board and to have an interesting cost at launch as well.
Geostationary satellites orbit the Earth at a distance of 36,000 kilometers. Even at light speed, a signal down below needs 500 milliseconds to reach a satellite. That's half a second. That delay, or latency, during phone calls means that the people talking constantly interrupt each other. In order to ensure a smooth online gaming experience, that time has to be under 100 milliseconds, while a delay of just 20 milliseconds will cause orchestra musicians to fall out of sync with each other. With effective internet reception not possible with current geostationary orbits, the satellites need to be brought closer to what is called low Earth orbit. Companies planning to install satellite constellations include OneWeb, Google's SpaceX, and Amazon's Blue Origin. The closer a satellite is to Earth, the smaller the terrestrial surface it can reach, which is why it would take hundreds, if not thousands, of smaller satellites to cover the entire planet. And that's a problem alone in terms of sheer production capacity. The consortium led by OneWeb also includes Virgin Galactic, Airbus Defence and Space, and tech giant SoftBank. Together, they've pooled close to $3.5 billion to make the dream of global internet access a reality. Airbus has provided its specific expertise to enable the mass production of satellites.
That was a big challenge. In fact, as you know, we are really experimented in let's say, geo, so big satellite production. But for mass production, it was a challenge to provide satellites in a few days compared to here, where we have like here in Toulouse, the integration takes around 9 months, and 3 days was really crazy for the market. And so today we developed a lot on OneWeb satellites facilities.
Capacity is currently at 1 satellite per day. OneWeb plans to launch its global service in 2021 with 650 satellites, orbiting at an altitude of 1,200 kilometers. The next step involves the constellation being expanded to more than 2,000 units, which has in turn required the development of completely new production methods. Roch Desrousseaux is a test engineer. He oversees a production setup that manages with a minimum of human input. The newly designed propulsion systems are also built here in scaled-down versions. The fuel tanks filled with xenon gas are provided by an unexpected source.
Here is how the spacecraft is going to move from one point in space to the other. For instance, the rocket is going to put the spacecraft at a certain altitude, but then the satellites need to reach a much higher altitude. And the way it's going to do that is by using a thruster. So it's an electrical thruster. This tank, so normally it's used for firefighters. It's designed by a company that didn't really know how to do space, and it's much cheaper than more traditional tanks. Once Sebastian is done with all the assembly, again, we really want to avoid human errors. So the way we're going to do that, we're going to take a picture with these 2 cameras here, and the pictures that we're going to take, they will be compared to a reference picture, and based on the 2 differences, we'll be able to say if Sebastian has done a good job or not.
With human error essentially ruled out, high-volume production is possible with short turnaround times.
When you're doing 900 satellites of a kind, it's easier to get cheaper than the recurrent price. In terms of testing, we are doing less testing, so you need fewer people, so it's cheaper. And the order of magnitude is maybe like a bit more than 100. Like if you want to buy this satellite, it will be roughly $1 million. And if you want to buy a geosatellite, it will be way more than that.
OneWeb and also Google, SpaceX and Amazon plan to offer their internet services everywhere on Earth, in the process getting 4 billion people online. London-based OneWeb has an official licence from the country's aerospace authority and sees itself on a mission to bridge the digital divide. The company's current and potential future clientele includes banks, airlines, shipping companies, industry, disaster relief agencies, and the military. End consumers will initially be able to book the service via local telecom providers. And, as already seen in the mobile phone sector, the price will be lower in Africa than in Germany, for example. Mike Lindsay previously worked in systems engineering for NASA and is part of the design team for the OneWeb satellite constellation. The company was the first among the competing consortia to receive approval from the International Telecommunications Union, a United Nations agency. And that license is absolutely mandatory for providing the service.
The OneWeb system uses radio frequency spectrum in order to send information to customers to provide this broadband internet connectivity. You need spectrum. It's a span of radio wavelengths in order to transmit information at high data rates. The more spectrum that you have, the more data that you can provide. And because you and I are used to these broadband speeds of being able to stream video and send information very quickly back and forth, we need a lot of spectrum in order to provide that type of service to so many people.
Designing a constellation of satellites in constant contact with each other and the Earth is a complex undertaking. It involves a number of technical processes to function at the same time, processes that have no precedence. The brain of the constellation, the Ground Network Operations Centre, is in London. It's headed by Alan Hewitt.
And at OneWeb, we're responsible for looking after the ground network. So we do two core functions. First of all, we provide situational awareness. So we look for anomalies in the ground network. Where they occur, we work to resolve them as quickly as possible. And secondly, we do what we call a resource plan. And the resource plan is really the brains of how the system works. This brings together the ground network, the antennas, the spacecraft, and the payload and the actual user UTs.
The ground stations run automatically and are fitted with 30 antennae, each maintaining contact with 30 satellites. There are currently just 2 fully functional stations, one in Spitsbergen, Norway, and the other on Sicily. For complete global coverage distributed across the planet, you would need just 45 ground stations, all interconnected.
Very quickly, as you say, we're going to be scaling up. Come Q2 next year, we're going to be adding 3 ground stations every month. So that's a huge ramp up to what we're doing today. Today is all about testing and integration. Next year is all going to be about bringing those ground stations into service.
The ground stations always seek the best possible connection to the satellite that's closest to the user and can provide the best possible bandwidth. The relevant signal shifts from one satellite to another, with the user remaining blissfully unaware. The OneWeb consortium is currently ahead of rivals Google, SpaceX and Amazon, and by the end of 2021 it hopes to have a constellation numbering 650 satellites. Either way, the Earth's orbit is set to get a lot of traffic in the near future. How will the engineers ensure that there are no collisions?
So something we're doing at OneWeb is actually enhancing our safety by separating each plane in the constellation. So there are multiple planes of multiple satellites each. And if they're all at the same altitude, you have this sort of crossing point where satellites are zipping past each other at very high velocities. So what we do is we separate those crossing points so the satellites are actually not zipping past one another. And what that means is we're actually, in some regards, we only have to manage a single plane at a time. And you can apply that same principle to other constellations. So we are maintaining many kilometers of separation between SpaceX. SpaceX is separated from the Kuiper, the Amazon constellation. And that's a very important safety detail to make sure that operators are not trying to launch and operate hundreds or thousands of satellites within the same amount of space.
Satellite constellations are not the only inhabitants of Earth's orbit. There's serious traffic in immediate outer space. In addition to countless disused satellites, there are spent rocket elements, fragments of exploded spacecraft, and other space debris circling the planet. The result is a growing orbital scrapyard, now comprising 20,000 objects with a diameter of 10 centimeters or more. They're joined by 700,000 smaller objects of at least 1 centimetre in size. And the speed at which they move makes them extremely dangerous.
So if there is a collision in space, it can be catastrophic. Objects in Earth orbit are typically traveling around 25,000 kilometers per hour. And even a small object, say 10 centimeters, can carry enough energy to fragment a large satellite into thousands of pieces. And so if such an event occurs, now you go from one satellite and one piece of debris to thousands of pieces of debris. And each of those pieces of debris might carry enough energy to, again, fragment a different satellite. And so, there's this fear of this sort of chain reaction where one collision creates debris. That debris strikes another satellite, creating even more debris. Actually, I don't know if that's the case, but I'm just going to say.
There are still no rules on the behaviour of satellite constellations, whether traffic-related or on safety or ethics. The only stipulation is a ban on stationing weapons in Earth's orbit, and that the satellites have to be safely deorbited after 25 years. OneWeb has decided to let its satellites expire in the atmosphere after an operational life of just 5 years. The major space-going nations are working on sophisticated near-Earth radar systems to prevent satellite collisions. Germany's aerospace centre, the DLR, is using a missile defence system from the German military in conjunction with the famous Fraunhofer Gesellschaft research group. The TIRA radar facility outside Bonn in western Germany is the only one in Europe that can track and depict objects in orbit up to 2 centimetres in diameter. Manuel Metz and his colleagues have been conducting precise measurements on space debris in order to prevent the need for evasive action by active satellites.
If you have an object that you are especially interested in because it is threatening to collide with your own satellite, then you can use this system to remeasure its orbit and obtain more precise data. That gives you a better risk assessment, whether a collision is actually imminent or whether such a collision can be ruled out.
There are several collision alerts every day. Evasive manoeuvres are only needed 2 or 3 times a year. But the scientists' models project a collision in orbit triggered by space debris every 5 to 10 years. Just how crucial this surveillance is became clear in early September 2019, when a satellite in the SpaceX Starlink constellation was approaching a weather satellite belonging to the European Space Agency. ESA tried and failed to persuade SpaceX to take evasive action. But with no response from the American company, the agency had to force its €400 million weather satellite into a collision avoidance maneuver. Whether SpaceX was unwilling to take action or incapable due to a lack of control over the satellites remains unclear.
Provided the systems work really well and have a very high level of reliability, operating these satellite constellations is no problem. But once we get into an error rate in the range of 10 to 20%, things start to get really critical. Then these constellations can become a problem within themselves and between each other. And that can lead to a cascade effect where more and more space debris is created.
The Wachtberg radar facility near Bonn is among the leading lights in space surveillance. The TIRA radar has a limited range of sight. It has to be told approximately where an object is in the sky in order to conduct precise measurements. The TIRA facility is immense compared to the German experimental space surveillance and tracking radar, or GESTRA, a new electronically controlled radar system that observes the near-Earth zone of space within milliseconds. Based on semiconductor technology, the radar will be the first in Germany to track active satellites and space debris 24/7, while also creating an orbit data catalogue that helps to prevent collisions. Gerald Braun is in charge of Germany's Space Situational Awareness Centre, which will work together with GESTRA on data collection. He's seriously concerned about the satellite constellations currently being assembled.
Das Problem bei der Sache könnte sein, dass die OneWeb...
There could be the problem that the electric drive systems in the OneWeb satellites do not allow high delta Vs, or speed increases.
Ermöglicht. Und der Plan ist, die Satellitenflotten auf einer Bahn...
The plan is to deploy the fleets in an orbit of around 500 kilometers, and then slowly boost them to 1,200 kilometers through the most contaminated belt, and then bring them back down at the end of their lifetime.
Und auch wieder nach Ablauf ihrer Lebensdauer.
It's a problem similar to sending a family of snails across a major road during rush hour.
Ist ähnlich, wie wenn Sie eine Schneckenfamilie zur Hauptverkehrszeit über den Kölner Ring schicken würden.
There's a major risk of collision, not least because the electric propulsion systems do not give the satellites much scope for evasive action.
Mit dem elektrischen Antrieb nicht sehr ausweichfähig sind.
The data from the TIRA radar system and from GESTRA are collated at Germany's Space Situational Awareness Centre in Udem, near the Dutch border. The German Armed Forces and the German Aerospace Centre work together at the NATO Communications and Information Agency unit there. Radar systems can only track the near-Earth zone and not geostationary orbit. So the centre also uses telescopes to surveil satellites that are higher up. And there are already concerns on the ground over the first satellites launched by SpaceX's Starlink constellation.
What we saw from the launch of the first 60 Starlink satellites is that the brightness is relatively high. And that can lead to interference to observations in near-Earth orbit. That's the problem feared by astronomers, that a growing population of tens of thousands of mini-satellites in the low and medium Earth orbit will reflect the sun's rays onto Earth. And in those areas of observation, telescope coverage will be compromised.
Not surprisingly, some of the traffic in the low Earth orbit is from military sources. The relatively close range of 500 to 800 kilometers is a convenient one for gathering meteorological and geological data and for spying. Nowhere else in Germany do the armed forces and the civilian German Aerospace Centre work so closely together.
Here we can see the OneWeb constellation, with 6 satellites launched to date, all on one orbit. This is the Starlink constellation with 10 times the number of satellites, spread across different orbital planes. And this constellation is likewise set to grow significantly in the future.
The large number of electrically powered satellites being introduced into critical orbit heights will definitely pose questions.
In the final phase of the satellite's deployment, this will also present bigger challenges for global surveillance systems than is the case with the current population in orbit. So we have to prepare accordingly and continue to expand our capabilities.
The importance of protecting critical infrastructure such as weather, GPS and observation satellites was highlighted in March 2019. The Indian military shot down one of the country's weather satellites in order to demonstrate its strategic space capabilities. The satellite broke up into 6,500 pieces of debris, which then spread around the globe at a speed of 35,000 kilometers per hour.
The interesting thing in this area is not so much the mass of debris parts that stay on the original orbit as the parts moved upwards by kinetic energy, which will of course pose a threat to other satellites.
China has also demonstrated its ability to destroy critical infrastructure in low Earth orbit. Dongtan in South Korea is just a 2-hour car drive from the border to North Korea. Everyone here is aware of the threat from the North's missile system. And it's here that OneWeb is working with Intellian, South Korean specialists in maritime satellite communications. Intellian is making the satellite antennae for the ground stations and user terminals that can pick up and relay the signals from the satellite constellation at any point on Earth. The Koreans were chosen due to their experience in maritime communications, where the transmitter and receiver of signals are both moving. The idea is to adapt that technology for internet access in self-driving cars. Permanent connectivity will become increasingly important. Steve Cha and Kevin Eom are the visionary minds behind Intellian.
The maritime geo is still challenging, but we have all the solution now. So geo is fixed. But I think a vessel is moving. So that means antenna should move and also maintain, track the satellite. That's the key algorithm we are developing using now. But LEO is additionally, satellite is moving. So that means we have two motion, like by ship or by satellite. So that means, but also the accuracy. So even though the worst cases, but we have to very accurate track the LEO and then we can maintain the connection. So that is could be our challenge for near future. So we'll try to overcome.
Rotating parabolic antennae are at the cutting edge of current technology. But a few years from now, there might well be new antennae available based on semiconductor technology.
This is completely different with a parabolic antenna, but this is a real future antenna. But this one is no mechanical body. It's like we can put here, and then there is some electronic circuit inside it. Electronic circuit is steer real beam, and then track the satellite itself. So this kind of antenna doesn't need the mechanical motion, and then it's very accurate track, and also it will be very small type of antenna.
Whether by sea, land or air, the idea is to ensure easy connectivity for people using all means of transportation, in addition to those who are stationary. This facility near Seoul tests radio communications with objects in the Earth's orbit. A group of engineers, headed by physicist Nav Baines, spent several months focusing on one specific task, proving beyond doubt that an internet connection can be established on 90 days in a row via a satellite constellation. Their test results would determine whether OneWeb's rights to transmit at the frequency spectrum approved by the International Telecommunications Union would be confirmed. It's a milestone the team eventually reached in 2019.
Our satellites were launched in February of this year, and we want to show that proof of concept that it works. So we want to be able to send signals up to the satellite, back down again, and prove that we can send traffic at very high speed and therefore realize some of these services, high-speed broadband services that we want to offer the world. So this is a perfect testing ground. We've got regulatory clearance here to do transmissions and receptions.
Could a system initially comprising just 6 satellites in orbit stream internet video content from Germany? Nav Baines and his team were also eager to see how the experiment pans out.
What we'll be doing is we'll be going to the ZDF channel, RISAT, and getting content from there over to our KA terminal modems, onto the KA terminals themselves, up to the satellites, back down again, and then all the acknowledgements coming back across the internet so we can keep on streaming. Yeah, we just got 3 more minutes, and then the satellites will be coming over. Yeah, each satellite flies over. It takes about 3 minutes, and then the next one, then the next one, next one. So, okay, 10 seconds. Yay.
Okay.
We're now live streaming video from the ZDF channel. It worked briefly. The quality of the signal wasn't good enough, and so it lost the connection. Okay. But we can retry, and we're still in testing mode. We're testing the satellites out, optimizing the system to get better and better performance, better latency, and improved quality of video over the satellites. Okay, well, thanks everybody. Good job.
But providing sufficient bandwidth for streaming videos in full HD will require the launch and deployment of far more satellites and more ground stations. Over in the United States, OneWeb has a second ground station not far from Washington, D.C. The constellation's satellites can be controlled from here and from headquarters in London. Daria Carini is responsible for coordinating the constellation's flight maneuvers. She and colleague Naya Ritchie control individual satellites. Here, the 2 experts are conducting extensive tests connected to automatic control routines.
It's a system that I want to trust, but at the same time, as a human, I want to make sure I'm checking all of my checks and balances, making sure that everything is okay with the satellite before we proceed to the next step. Because again, this isn't a simulation. We have to take our time, and we have to be as humanly perfect as possible.
How many controllers will be required to pilot a mega constellation of several hundred satellites? This is where artificial intelligence will come in to assist the human operators.
I believe we're going to be having 1 controller for about 20 or 30 satellites, maybe even more. We're trying to automate our system so that 1 person can handle as many satellites that is needed within our crews because, like you said, we're not going to have a 1-to-1 ratio, and we need to learn to automate our system so that when we see issues on board, if our pilots can't do it manually, then automatically our system should be able to handle it.
It's kind of a walk before you run type of, philosophy. So instead of having so many satellites up at first, we deployed, 6, and then we could spend a significant amount of time kind of getting to know them, like a new friend, basically, just deciding, this satellite is capable of this and it's not capable of this, and I kind of adapt to the constellation as it grows too, because of our ability to understand the vehicles for months. We've, since launched for about 6 months now, and we have gotten a good idea of the types of tools that we'll need in order to, sustain a mega constellation.
And in addition to the technical challenges, there are also no end of regulatory obstacles to overcome.
Somebody's fixing that. All right. All right. Let us talk. This is good. Thank
Ruth Pritchard-Kelly and her team are trying to convince more than 200 different countries and territories to grant OneWeb permission to provide services.
Every person in the world wants access to information and entertainment, and they may define that differently, and their country may be concerned about what access they have. But even a country like North Korea wants their people to have access to certain kinds of information, right? And so every country in the world wants their people connected. They may want to control the way they're connected, they may have concerns about data protection or security, but they want their people connected. And so even North Korea, even Cuba, even India, China, Russia, they're all interested in connectivity. Connectivity is the key to the future.
Internet access in North Korea, China and Russia is regulated differently than in Germany. What surprised the company was how more democratic nations also tend to demand an emergency off switch before giving approval to internet access via a satellite constellation.
You know what? Even the United States asks for an off switch. Every country wants a little control over the traffic in its country. And one of the things they say basically is if you cause interference, usually, you'll need to be turned off. And you say, of course. And the idea is, I'm never going to cause interference, right? I'm going back to the coordination with the other satellite systems. I don't want to have to turn off, so I'm going to make darn sure that I'm not interfering into anything.
OneWeb and its rival Google SpaceX are currently neck and neck in this new space race, with Amazon lagging some distance behind. Whether high-speed internet from low Earth orbit will actually be commercially available by the end of 2021 is still hard to say. South Korea has the fastest mobile internet on the planet, and practically everyone here has high-speed connectivity via terrestrial or mobile networks. And it's here that Nav Baines and his colleagues are working towards a future where every person on Earth could have fast internet via satellite, provided their governments allow it.